to introduce you. So, all right, go ahead.
Okay. Yeah, so I will just briefly start my talk with a very brief introduction of me for the YouTube audience. Yeah, so my name is Yang. I'm from University of Hong Kong. Now I'm doing research in hydrological modeling. Mostly I use machine learning for solving prediction problems. Okay, so today I'm going to present a paper from around 10 years ago called Deep Compression, compressing neural networks with pruning, trend quantization, and Huffman coding. So in this paper, they introduce a way to make the neural network smaller. Here is a presentation. So because it's a discussion, just stop me or ask questions whenever you have. I will be happy to discuss with them. They discuss the questions with you. So the overview of this presentation is like we follow the paper briefly, covering some part I consider important, but they may not be very important to others. And I then present some applications in hydrology, which I run some simple experiment to compress LSTM models. I have a few questions to lead us to discuss if we have time. And finally, I will give the conclusion. So the paper of today's discussion is this one from Han, Mao, and Daly from around 10 years ago, an algorithm called deep compression. Okay, so the background, which is neural networks are getting more and more popular 10 years ago. They are everywhere now. They are powerful, but very resource intensive. So the problem is to deploy them on embedded or mobile system with limited storage or limitations of energy. So they want to conserve battery. Yeah, but in nowadays context, because of the rise of large language models, we want some large language models that are still so large to be able to run on our local computer or local servers. So this is also one of the motivations for compressing models. So the solution to this problem is called model distillation, which is the process of transfer knowledge from a large model to a smaller one. This can be train a student model following a large teacher model, or by pruning some of the unimportant weights of the large model to make it smaller. So there are several ways of doing this. The paper proposed a method called deep compression. So model compression is also relevant to hydrology because it helps us to understand the complexity of the hydrological processes. So basically, we want to understand how many parameters we need to describe a hydrological process. And it can also be useful for modeling, for modeling theory. So whether a model with fewer parameters are more reliable or more interpretable. So this is so these questions are unknown to me. So I want to discuss them with you toward the end of the presentation. So the challenge of compressing a large model is that there's memory constraints. So from 10 years ago, an image model, AlexNet, can require up to 200 megabyte, and another like VGG model can require up to like half gigabyte. A large language model nowadays can require more than 500 gigabyte, or even more. So there's also constraints on the power consumption because some people want to have privacy. So they want the model to run on their local computer and local mobile, which requires a smaller model because to access the data from the disk or from other device is much more power hungry than just directly process them on the chip, on the computer chipset. And also we want the model to run very fast because we want to know the answers immediately. For example, for car, for driving cars, we want to understand the situations in real time. So the opportunity is to do compression, so we can do on-chip storage and energy saving. The goal of this paper is to provide a method which can reduce model size while maintaining accuracy. So this algorithm is a pipeline of 3 stages. So the first is pruning. So it removes unimportant weight from a large network. Second is called trend quantization. So this one is to reduce the position of the weights or use less memory to store all the weights. The third is Huffman coding, which is a classic technique used in information theory for compressing information or messages. Let's look at the method one by one. The first one is pruning. So pruning removes weights that have little impact on the model's performance. So in this paper, the author used a method called magnitude-based pruning method. So basically, they train a model normally, like a large complete network normally. Then they remove the link, like the weights of the network, which has smaller magnitude compared to the rest of the network. By turning off, they manually set the weights to 0. Then they iteratively fine-tune the model with fewer connections. Go ahead.
So Yang, in your reading, did they learn the threshold on the weight, or they just arbitrarily chose it themselves? Because it seems like another thing that could be learned in principle. Yeah.
Yeah, it's a good question. So in the paper, it does not mention the technical details.
Okay.
It plot some like distribution of the weights. I think it's select based on percentage, and it's an iterative process. How many iterations, I'm also not sure.
They
But
choose the threshold based on how many weights they want to remove, and then they,
yeah, then
okay,
they effectively update the weights. So
okay,
it's like some flexibility in terms of if you want to remove the weights once or like 100 times, like half 1% each time. Yeah,
okay.
a multiple way of doing that. Yeah, so we just report the basic principle. Okay, so
Every
let's,
every time they remove the weights, they then run some training to update the remaining weights.
yes, that's true. Yeah, but this process is very flexible, so we can adjust the time needed, the number of nodes to be removed, and the number of training iterations.
Okay.
I saw one question in the chat. Okay, so it's the link we can check out later. Okay,
Choosing to
so
remove. Okay.
so for pruning, so they were able to reduce the size by 10 times, which is like 10% of the original memory needed for storing the network, and 13 times of compression compared to the original model with minor drop in accuracy. So AlexNet and VGG are networks for classifying images. So it's trained on ImageNet for classifying the object of an image. Okay, so the second method the author used is called trend quantization. So trend quantization basically is to remove the number of effective weights by having multiple connections sharing the same weight. Then they fine-tune the shared weights. Okay, so instead of like each connection has a unique weight, is assign identifier to the connections. There's only a limited number of identifiers. So the option that a link have to the weights is minimized.
And this is done by clustering.
It's done by clustering. I will show you how they do it. Okay, so they are using a k-means clustering method. So basically, they train a network. You have a network, whether it is pruned or original network. You can cluster the weights to a smaller number of groups, like 1D clustering. You just arbitrarily pick some random starting points and try to identify the clusters. So basically, each point in of the weights are associated with one cluster, and you then use the nearest cluster center to replace the original value. So instead of having original value, you are assigning the weight to its closest cluster center. So it is also trained through backpropagation. So here is a nice illustration. So in this matrix, we show a 4 by 4 weight matrix. So each number represent a weight associated with a link. For example, this one is like link between node 1 to second node to the second layer, node number 1. And this is the weight of the connection between link node number 1 and node number 2 in the second layer, etc. So then you can cluster, for example, here as 4 clusters based on their value. So you can see that the blue color are around 2, the value are around 2, and the green color are around -1. So they belong to the same cluster. So instead of having to store the original value, you just store this index matrix. So for example, here, this color, this number 2.09 is replaced by the index 3. And we have a lookup table for storing the corresponding numbers to cluster number 3. So this is called quantization. So after having this table, we can further optimize the parameters using training, just as training a neural network. So what they do is they calculate the gradient of the loss with respect to the weight as euro. So this is a gradient matrix. Then they cluster the gradient based on their original clusters in their original weight. Then they reduce them, which is a fancy way of calling average. So you average them to a single number, which is a required adjustment made to the cluster center, the centroid. Then you times the linear learning rate to update the centroid of the original centroid step by step. Yeah. So this is how you update the values of the clusters. Okay.
Oh,
So
sorry,
this
sorry. Can I ask a question about this?
yeah.
Were they able to establish a connection between the initially, like, I guess the centroid is the difference between, like, if we take the blue example,
Mhm.
2 is it's the middle distance between 209, 212 and the rest. D like, did they establish a connection between the initial centroid that is the average distance and the fine-tuned centroid? Like, is there a statistical meaning to how the fine-tuned value is achieved?
Okay, so in the paper they do discuss the importance of choosing a good initial centroid. So what they found is that random is not very good. So you
Mm.
want initial centroid to be as spread as possible. So like a uniform distribution as the starting centroid may be good. So
Yeah, I think my question was more, did they find any reason of why 1.96 makes a better sense than 2, and why did the fine-tuning achieve that value?
okay, so this is so you ask why 1.96 is better than 2?
Yeah.
Yeah, so basically you have to calculate the loss of the network in their reduced form. So
Oh,
basically,
okay.
yeah, then you update the weight such that the model is perform better.
Oh, okay. Okay. Thanks.
Yeah, but you might have to do like the reclustering if you update the centroid, maybe.
Okay.
Yeah,
Thanks.
I think there are some flexibilities in the implementation. Yeah. Good questions. Thank you, Anton. Okay, so let's continue. So train quantization is shown to be a very effective method in reducing the number of bits needed to encode the data. So given K clusters, we only need log K to the power of 2 bits to encode the index. So the number of weights required to represent all the weights is only n times log 2k, which is the number of bits required to store index, times k and k times b, which k is the number of clusters and b is the number of bits required to store an original value. So in contrast, the original storage requirement is n times b, which n is the number of weights, and b is the value is the storage required for storing an original value. So they can calculate easily a compression ratio. So they found out for AlexNet they can use only 8 bits, which is like 200 shared weights, to represent each convolutional layers, and only 5 bits for each fully connected layer. So it's quite effective by reducing the number of shared weights, number of weights required. And this is then they have the third trick to reduce the footprint of the model, which is called Huffman coding. So basically, they are basically they are using Huffman coding to encode the index required to store the store the weights. So for example, many of the weights are associated with cluster 1. So cluster 1 can be associated with a smaller prefix-free code. So that is optimum. So, but Huffman coding is quite classical way of storage, storing image information. So yeah, this is not a main selling point of this paper. Some example from the paper, they found out weight index somehow have screw distribution. So for example, many weights are number 9 in the cluster of number 9. So they can use a small code to represent number 9. So it can be short in the memory. So the overall result of the model is quite good. So they compare the prediction error between the compressed model and the reference original model. They observed minor drop in the prediction error. Sorry, or increase in the model performance, because it's a drop in model error. So it can somehow even improve the model performance. Yeah, the same is true for the image model. It can reduce the prediction error, and they can achieve quite surprising compression rate. So you can compare the original model, which is 240 megabyte, to only less 6.9 megabyte, like 35 times reduction. So now the model can run fast in your cell phone or other mobile device, which the original model cannot. And the model achieved similar or even better performance compared to the original model.
Let me just comment about that. It might seem surprising, but if you think about the fact that you're actually reducing the dimensionality of the search problem dramatically, because you're reducing the number of weights, the weight space you're searching in. So the first place is just figuring out what's that dimensionality reduction, and then search is much more efficient in a lower dimensional space. So it makes sense that you could get improvements.
But Ocean?
Yeah.
But I think the main problem is, and I think this is something was like noted when they were kind of training DeepSeek from ChatGPT, is that if initially you start with a smaller set, you will not achieve this performance. You have to start big and then
That's right.
kind of start pruning it.
That's what they did, right? They started in the big space, and then once it converged, then they figured out what the dimensionality reduction was.
Yes.
That makes sense. Yeah. Thank you.
Thanks for comments, Osher and Mahmoud. Okay.
I mean, that's, sorry, one more comment. That's essentially equivalent to doing a sort of a prior, right? Because you don't know what your initial values of your weights should be. You don't even know in what ballpark they should be. So that initial part is essentially setting the prior on your second stage. Yeah.
Yeah.
Okay. Thanks for the comments. So let's continue. Yeah, so the author also looked into the details into the number of bits can be saved for each layer. So for example, this one is LearnNet, which is a classic convolutional network. So for each convolution, oh yeah, this is I'm not sure. Yeah, the LearnNet, some LearnNet is fully connected. I think this is one is fully connected version, fully connected 300 neuron in the first layer, 100 neuron in the second layer. I think this is a fully connected version of LearnNet, but I might be wrong. So basically, they found that you can achieve different level of reductions at each layer, and so the P means the weight compared the number of weights compared to the original weights after applying pruning. So like 10%, around 10% reduction for the first layer, and 9% for the second layer, and
not percent reduction. That's the amount left, right?
yeah, amount left. Yeah, sorry. Yeah, this is amount left. Yeah, compression level. Yeah, amount left. Yeah, 26% for the final layers, and they found the number of bits required to store the weights using a quantization method, which like 2 to the power of 6 numbers are needed, unique values or clusters are needed for storage of the weight, the cluster centroid. So these weights can be this number of bits can be further reduced by using Huffman coding, and the index bits required is to store the mapping between the locations. The mapping between the clusters, the cluster index. Yeah, so basically it's the number required to store the cluster index. This can also be further reduced. They also did a comparison for convolutional network. So the findings are somehow similar, but you can also observe some difference for certain layers. So this is a detailed result. Yeah. So finally, they compared the different compression levels and compared to the singular value decomposition method, which is conventionally used for reducing the number of weights required for a network. So they're compressing.
Yang, just a quick question. In the last slide you showed, as I think one before that. Yeah. Do they comment on the fact that, no matter the size of the layer, you get very similar bits required in the compression at the end? So that seems kind of interesting. So the third layer is, smaller than the other two, but all of them require 6 weight bits. And same thing for the second weight bits column.
Okay. Yeah, nice observations. I did not recall the author mentioned that, but I might miss the point. Yeah, so they might have already reported it in the paper. So I have to double check to confirm.
If I remember right from his lectures, different layers needed different kinds of compression. But then, of course, you have to go through and try so many different kinds of combinations.
Okay.
So in principle, each layer could be compressed at a different rate. But if you want to keep things simple, you can also just use the same number of bits per weight. So it depends on how much effort you want to put in. Yeah.
I just have a comment on that. I don't know if it's relevant, and probably it's nothing related, but depending on the activation functions, the value of the weights are capped. Maybe it's linked to the value range, like 6 bits is maybe the most you can achieve if it's between, I don't know, two values.
Well, the number of bits has to do with the precision you need. Okay, so if you need more precision, then you need more bits. So that's really what it boils down to.
Yeah. Okay, I think the comments make sense. So yeah, let's continue. Okay, so this is a like summary result they report in the paper. So they compare different strategies, whether it is pruning time together with quantization, pruning only, or quantization only. So and the conventional SVD method. So what they found that is that you can achieve very good compression with pruning together with quantization, and with very little or no drop in prediction accuracy compared to perform them alone. So this is an interesting result. So yeah.
Yeah, I think it's interesting, but let's also keep in mind that we're talking about a classification problem. And classification problems are basically boiling down to yes, no, or
Yeah.
selection between many. So you should expect, you might not get the same performance on a regression problem.
Yeah,
Yeah.
that's true.
But I still think it's highly impressive that you can reduce a model to 3% of its, or 4% of its original size after training it. I think that's really quite remarkable. And it makes sense that pruning would be more efficient than quantization first. Yeah.
Yeah. They also then go ahead to make some more experiment to see the number of beats. Like they select a number of beats, like the number of effective weights needed for each layer, and they have applied quantize only, quantize plus quantization. So they have an explanation is that they found, so first they found like pruning does not hurt quantization. So if you look closely to this chart, like for example, the first one, so you can see a dashed line very closely to a solid line. So this means if you perform quantization only, and you perform quantization plus pruning, the model will have similar performance. So this means pruning does not hurt quantization. So they explain that their explanation is that pruning network have fewer weights, so quantization can be more accurate. Like the class center are more, so they have so they can have like more accurate clustering algorithms. So yeah, I found this explanation not very easy to understand, but I'm still digesting on why this happened.
Well, what's interesting is how few bits you need before performance drops off.
Mhm.
And the other thing that jumped into my mind when I saw this was, let's say you just averaged everything and you said, I'm going to use 4 bits or 5 bits. So 2 to the 4 is 16, 2 to the 5 is 32. That actually suggests that you could just as easily use genetic algorithm and do a quantized search in a random search in a space and not have to worry about fine tuning of the weights more than 1/32th of the weight range. So this opens the door, I think, to growing neural networks using things like NEAT and other things, which is a method we need to discuss.
Okay, very interesting comments. Okay, so yeah, so the paper then goes on talk about the energy savings and efficiencies of the computational resources needed. I did not go in depth into that. Instead, I run some experiment with LSTM, which is a classical method for random modeling. So let's go ahead to LSTM networks. So LSTM networks are commonly used for modeling sequence data. So those are the basically LSTM network have the equations look as the following. So they have different gates. So basically 4 gates functions controlling how much new information is added to the system and how much information is being outputted at each time step. So the 4 gates work in similar fashions, like taking the input from the current time step and some values which is associated with output from the past time step. So it has a forget gate, which is the information need to be ignored or discarded or removed in the next time step. And the input gate, which is processing how much information is being added to a system, and a candidate cell state, which calculates the information being added to an inner cell of the network, which is carrying information along the way, rather than just directly outputting it. And it also has a output gate, which is calculating the actual information being outputted from the cell. So it's quite a complex network. So the number of parameters required for LSTM layer can be calculated using the following equation. So basically we have 4 gates, which has four matrix. So the dimension of the matrix associated, like we can see that so basically you have for each gate we have a W and a U. So W is associated with the number of input at each time step, like the dimension of the forcing, for example, in hydrology at each time step, and n hidden, which is the dimension of the cell state. It's like the dimension of your model, the hidden information you carry along at each time step, and n hidden is the number of the weights you output from each gate. So the total number required for W and U combined can be calculated using this equation. And unhidden is a number of biases associated with the hidden output node. So we can calculate using this equation. Let's see an example. So if we have a input dimension of 3 and number of hidden layers, number of hidden neurons to be 64. So we have over 17,000 parameters to optimize for the network. So this number is actually quite low. So in hydrology, people use like 2-layer LSTM with 128 neurons, with also some network added to LSTM for processing, so for pre-processing the data or for post-processing the output. Yeah, so they can grow quite dramatically. So the relationship is nonlinear, as you can see here. So it can like growing exponentially fast if you are increasing the number of hidden dimension, because you have a term which is hidden dimension times hidden dimension. So this like nonlinearity in that relationship. So I only ran one experiment with LSTM on one catchment, which is one catchment from Germany from the CAMOS DE dataset, which is a relatively smaller catchment with rich data. It has like 70 years of rainfall runoff data. We use 80% for training and 20% for testing. So I try to use different number of hidden units in LCM from 4 to 256. So all of them have quite similar performance. So I decided to use 8, which is a lucky number in China. Yeah, but nevertheless, it's a small network for easy analysis. So we end up to have only 384 parameters, and the input of the network is the past 1 year P precipitation, potential evapotranspiration, PET, and temperature, and the 1 day discharge Q as output. So I trained the model without fine tuning, just trained for 50 iterations, 50 epochs. The trend kg is quite high. The test kg is reasonable, although we found some overfitting, which can be resolved if you're using another validation set, or you do fine tuning of the hyperparameter tuning of the network parameters. So I applied pruning to the network to see the performance on, to see the effect on the performance. So the method I use is layer-wise pruning, performed by removing the weight with smaller absolute value using the PyTorch NN utilities prune this function. So this function can remove the weight associated with a layer of network based on their absolute value, like percentage you want to remove, you want to manually to set to 0. So notice that this function is only applied to the weight of the network. So they did not prune they did not fully turn off a node because the node has some value bias associated. So each node is associated with a bias, which is not removed using this method. So this is the out-of-box method provided by PyTorch. There are other methods can remove a node like fully by removing together the weights and also the bias. But I just stick with the simplest one now. So we can see the prediction accuracy drop rapidly if you prune like 10%. Sorry, if you prune like 50% the weights, the model performance will drop significantly. So this is without retraining. You just set some smaller values to 0 and see how the network performs. So with 30% of the weight removed, the model performed reasonably well. But if you remove half of the weight, the model have very poor performance, which is as expected. But interestingly, if you remove enough parameters, the model have better performance.
But
this
is without retraining, correct?
Without retraining, yeah. So this is the result I select for like 200 random 200 days for the discharge. The blue line, the black line is the observed value, and I only show the pruned hydrograph because the predictions are very close to the observations, the original model. So with the blue line, pruning ratio equals 0.1. The model have reasonable performance. Yeah, so basically, if you prune the model, they tend to predict a lower discharge, but it's not always the case. For example, if you prune like 30% of the weights, the model actually over predict the discharge. This may be because some of the negative weights or the weights contribute negatively to the discharge got removed. So the model become overconfident in the discharge generation potentials. So before removing 50% of the weight, like smaller compression ratio, you can see the model perform reasonably. You can still observe the shape, but just changing a magnitude. Go ahead, Hoshi.
I think this is an excellent illustration as to why we should not just use kg or NSC as a metric, but we should track all the components because, you know, the fact that kg goes back up could be misleading.
Yeah.
It may be because the correlation is going up, even though the other part's not improving. So I think, strictly speaking, we should track all three components or
Yeah.
more than that. Yeah.
Yeah, I agree. Yeah, so if you have a very large compression ratio, you can see like 0.9, so it almost always predicting a constant value, which is apparently bad.
Dan?
Yeah, this is really interesting. And my question is, I wonder, like, each of these series that is shown here, what does, I guess, maybe I missed the number in the ensemble. Like, is this a result of an ensemble? And what would the confidence interval look like on each of these if they're representing an ensemble?
Okay, so in this figure we show the result obtained for different pruning ratio. So 0.1 means we remove 10% of the weights from the network.
Yeah.
0.3 is 30%.
But it's a deterministic model, Dan. He's
And
just
it's a model, it's not an ensemble. Yeah.
he's running a single model. Yeah.
So this is a single LSTM.
Yeah.
Single LCM, yeah, but
Okay.
different version. In some version you turn off some of the weight to 0. Yeah.
Okay. But yeah, I guess my question is, or what I'd be interested in is, keeping these same pruning ratios.
Oh,
How much, like, what effect does the stochasticity and the initial weights have, and how does that relate? Because I mean, in my limited experience training the LSTM, the difference between the blue and yellow above and below the observed could just be simply the initialization.
yeah, I agree. So this is one deterministic model, and I prune the model only once without retraining. Then if we retrain the model and prune different version of LTM, the result might be different. Will be interesting.
It's also based on a single initialization, not several random initializations. So it's just preliminary. Yeah.
Preliminary result. Yeah. Okay. Okay. So this is a distribution of the weights of the LSTM gates. And so for each gates we have like n is the square. Sorry. Yeah, we have some equation to calculate the weight, number of weights. So basically you can see similar screwed distribution or like relatively normalized distribution compare which is similar to the author's finding. So you can use a short code to have an index for like this value, because they're 0, which is very common, but it got removed, also very commonly removed.
This is before pruning.
Before pruning, so you can effectively remove like the values around 0 quite effectively, because many values are centered around 0. They are all small values.
Right.
Okay, so this is showing the effectiveness of retraining the pruned model.
Wow.
Yeah, so after retraining, your model performance can get very good. But yeah, with very large magnitude of pruning, if you keep only 10% of the weights, the model never recovered. So you might need like 30% of the original weights.
But this is starting with a very small network. So
Very small network, and
even
I
with
only
50% reduction is still quite significant.
yeah, quite small network. I reduced by 50%, and also I only fine tune once. Like I remove all the weights at once. So you can do what you can do is like you remove 10% each time and fine tune your model it might have a different or better performance for the fine-tuned model.
And there's no clustering or quantization involved right
No
now.
quantization yet. I only do
Yeah.
pruning, but yeah, it can be also quantizations. Yeah, so one of questions I have is like why we prune the model. Should we just train a smaller model? So in this slide, I show the result obtained by training smaller models from scratch, like one LCM hidden unit and 2, 3, 4, 5, 6, 7. So you can see not necessarily increase in the test performance as shown in the orange color. So you need only 2 hidden unit. You can already model the system quite well. So
Luis, this supports your stuff.
yeah, and also Yuan's research MCP, which you only use a few neurons to model the system quite effectively. Okay, so in this one we compare the smaller model and the fine-tuned pruned model, but I did not plot them on the same figure because there are some caveats. So the bias are not pruned first in the pruned network. So it's not a very fair comparison comparing the prediction, the pruned amount, the pruned ratio, because we are effectively keeping the weights in the network. So if we are removing the connections all at once, might be a fair comparison. But overall, we can see same trend with that you can notice some significantly drop after certain threshold. Like from 1 to 2, you see a significant increase, and from pruning, it's like you can observe a quite significant drop in performance when you prune ratio move between 0.7 to 0.9. Yeah, but this is not a very fair comparison, as I mentioned. So I did not plot.
Sorry if I might ask, Yuan, you also, I think, found 3 to 5 nodes and no improvement after that, right? With your MCP?
What?
I think you also found that above, for the few cases you tested, you only needed 3 to 5 MCP nodes.
You mean in parallel?
Right.
In parallel, if not sharing information is 3, but sharing is about 5.
Okay.
Yeah.
Yeah. Thank you.
Okay. Yeah, so this supports Yuan's research. We only need a few neurons. Yeah. Okay. So yeah, so this is the end of the results and the paper. So we can have a discussion session. But I have prepared some answers, some questions, like 3 questions, but we do not need to follow. We can discuss any questions we like. Yeah. I also asked ChatGPT to come up with the answers. So we can see whether we can outsmart ChatGPT.
You want to give all the questions first, or you want us to go one at a time?
Maybe we go together. Yeah. So first one is why network pruning is effective. The second, why we are not training a small network from the beginning, and why we consider pruning is more effective than training a smaller network. The third one is related to hydrology. So are compressed hydrological model better? Should we have a large model? Large models can we prove large models are more robust or more like behave more normally under extreme conditions, like more safe to use basically, or under noise, whether they are safe? So these are 3 questions I want to discuss. I also want to know the answer, but we can also discuss other questions if we have in mind.
I can add a 4th question to that, Yang, if you don't mind.
Yeah, please.
Under what conditions would it be useful to have different levels of compression? It's related to your 3rd question, I think, because in some, for some applications, you might want a very compressed model and or be happy, and then in other situations you don't care so much. Yeah.
Mhm.
Yeah, LLMs are a good example. Quantization is fairly popular with very, very large models, but if you're trying to run like a huge model on a notebook, like on MacBook or something with 16 gigs of RAM, you can go up to 7 or 8 billion model if it's quantized to 3 or 4 bits. So compression level, because I want to say like maybe in LSTM the performance reduction is not significant, but in LLM, you definitely see a degradation between a full-size model and a compressed one with quantization.
Okay.
So compression could be interesting in this case, or depending on if you need absolute reliability with the problems we know with LLM, sure, but still it will degrade performance in some models.
So one of my main interests in this is, coming at it from a description length perspective, is that a shorter description is easier to understand in principle. That's a human bias, but because I can only hold so many bits in my head at a time. So I'm interested in short descriptions, and I think this is interesting from that point of view. But what I think is even more interesting is would be to add, so this would allow us to calculate the bit length, the description length of a model, right? Because basically every rectified linear unit is basically one yes/no question, and then you have a number of bits because you have to say where do I ask the question. So it's the point. So the bias term in the when you're going into a ReLU is effectively shifting the ReLU left and right and saying what's the threshold, the decision tree threshold at which I ask the question. And then the other bits have to do with the multiplying, what's the slope of the output. So in principle, we can calculate the description length of a machine learning model, and then we could calculate the description length of the errors. And in principle, this would then allow us to use the minimum description length principle as a guide to selecting models. But I also like the idea of trading off performance against model size and asking the question, can I reduce the model size to a point where I can actually try to understand what it's doing? Even though it's not perfect, it'd be more like a model which is used in the context of reasoning, right?
I think the comment is quite good. So I think for one of the advantage of smaller model is that it's easier for human to understand. Yes. So yeah, I also wonder like ensemble model can also be considered as a large model if it's considered as one model, but ensemble models can have much more parameters and they are proved to be robust in some cases. So one of the questions I have is like, can we somehow learn from the learn from the prediction of a committee of models just using a smaller network, like training a teacher student model out of a teacher model?
Right.
Yeah, whether it is possible or useful.
Oh, before we go too far, I wanted to point out that there's some similarities in what they did over here and what Luis did, in that he used a random forest to do clustering, and then he did k-means on clustering, and then he took the average values of the weights and then fed them back into the models and then retrained. So that there's quite a strong similarity here in the sense that instead of having separate weights at every catchment, you're now clustering the weights and then having clusters of catchments with very similar weights.
Very similar.
Yeah. But what we have
Okay.
not done, I think, is take advantage of the idea of things like Huffman coding, which is just beautiful to see, where it's basically because there's a bias in calculating description length using bits, which is that small numbers should have less bits than large numbers, right?
Yes.
That's a fundamental built-in bias, and it's implied in the notion of length. But if you can redefine your language so that each of your symbols has a bit length which is proportional to how frequently it's used, then you get a shorter description length. But it means you have to write the dictionary, which now says this value, which is what they did. So they have a weight value of 9 or 11 or something, but it's very frequent.
Mm.
So they redefine it using a symbol,
Yeah.
0 or 1 or whatever. So a smaller number of bits to represent that. I just really love that they did that. Yeah.
Mm. Yeah. Okay. Thanks for bringing Louis' paper. I think it's shares some similar ideas to the quantization and the clustering. Yeah. Very, very beautiful ideas. Okay.
What was your first two questions?
First two questions. So let's go to the second one. So why we are not training a smaller network from the beginning? Why we considering like model distillation is better than a smaller network?
I think, Sina, you basically brought that up. It has to do with the initial search problem, right?
Yeah, and I mean, one thing I would be very interested to see is that if the flow of information increases and we start including more catchments, would the pruning have the same impact or not? Because that's mostly the case, right? We are pushed towards doing regional modeling, and then instead of having like a bottom-up approach, we're doing a top-down approach for fine-tuning on the catchments that have limited data.
Yeah, that seems to again speak to the issue of how many catchment clusters do we need. So
Yeah.
Luis found how many clusters do you end up with, Luis? About 7 or 9 or something?
I'm pretty sure this depends really, because when I did analysis first was something around 5, but then when I did analysis using kind of a decision tree approach, really is something that you define because you can kind of cut the tree at different levels. So really it's not absolute number, depend of what you want to find or how much refine you want in the cluster.
But you didn't check to see how the number of clusters changes your performance curve, right?
Yeah, no, I didn't check that.
Because after a certain number of clusters, you might find marginal benefits. The CDF might stop moving to the right at some point.
Yeah, probably. Yeah, sure. Yeah, because when we defined the cluster, we were thinking in the interpretability issue, so trying to understand that. So in some moment, when I was increasing the number of clusters, you can see that the behavior is basically the same, that it's just changing a little. So I said, okay, I don't need more. For me, it's good enough. But for sure, yeah, it should be a number that is doing kind of a more optimal selection.
So a different strategy for hydro-LSTM would be to start with many more hidden nodes and then progressively try to prune it down. That would be interesting.
Yeah, sure.
But something I think I have seen, because I'm very focused right now on transfer learning strategies on like catchments with really limited data and different properties, is that not necessarily but the best regional model has the best transferred model is not the best transferred model. So that's a bit, I mean, that's a big problem. And we have not yet found the solution to it. So
could you say some more? I'm not quite following.
yeah, so you could increase the number of catchments and like let's say like generally to based on like an amount of data, the performance improves on unseen temporal data. But then if you want to fine tune it on other catchments, on other data, like do very like few shot learning, what we see is that not necessarily the best region, the model that use more information does not necessarily translate to the model that is the best fine-tuned model. which is interesting. And then what we found out is that a smaller model with less hidden units comparing two regional models, one with less LSTM hidden units had lower performance, but when we use it for transfer learning, it resulted in a better performance. So
one issue that Luis points out in his paper, which is close to hopefully being published, it's in review, is that the amount of information about space is far less than the information about time.
exactly.
So we may not yet be at a sufficient size of catchments, where we have enough information that we can say that increasing the number is not is actually not going to help anymore. Yeah.
Yeah.
I've had
The
this
other, yeah, go ahead.
I've had this nagging question for a while, and it's related to this starting network size. You think it's better to start with, say, a network of 1,000 8-bit weights and then prune down, or to start with a network of 500 16-bit weights and then prune down?
My reading of these results is that the bit precision on the weights is less important than learning the initial structure of the network. That the nonlinearities, the transformations you have to do in the beginning are more important than the precision of the weights. That would be my reading.
So are you saying that those two networks are kind of equivalent?
I didn't follow.
If you have both these networks have the same memory footprint, just
Okay.
different numbers of weights, right? So whether the question was whether you start with a network of 1,000 weights, 1,000 8-bit weights, or a network of 500 16-bit weights.
So I'm saying that I think if you simplify the network, forget about LSTM for a minute, just take a standard artificial neural network. You've got you've got three operations going on. You've got addition, multiplication, and rectified linear unit. And rectified linear unit is the fundamental nonlinearity in the system, right? So I'm saying that the fundamental nonlinearities, learning the nonlinear structure is more important. So I would tend to put in more nodes. This is my hypothesis.
Yeah.
I would put in more nodes with lower bit precision than the other way around, because if I don't put in more nodes, I have less capability of learning that nonlinearity.
Yep, that was sort of my guess too, but
Hmm.
right, I had no idea.
Because you're taking the number of bits and you're dividing them between the precision of the weights and the number of nonlinearities, right? So you're basically saying, do I allocate my bits to yes, no questions, or do I allocate them to precision? And the results of Yang's presentation today seem to suggest that precision would be secondary to asking yes, no questions. On-off switches.
Yeah.
I mean, that's like logic. Like logic is just all about on-off switches. There are no weights even in a logic gate.
Yeah.
The Hoshin's money is on a larger network with
In the beginning.
in the beginning. Yeah.
Okay.
Okay. We should find out through experiments for different tasks. Maybe it depends on the tasks as well. For classification, maybe Hoshin's right. For regression, maybe we need a precision.
But I don't think so. If we think in a kind of decision tree approach, at the end, if you are changing the precision, basically you are changing slightly the change in the splitting. But the splitting, the first thing that you need to know is where to split the data. So the precision there is going to be doing nothing, basically. The
That would
first is
be
you need to know what is the tree structure.
that would be easy to test, Luis, because if you took your inputs and you broke them into 10 bins, right? And versus 15 bins versus 20 bins versus whatever, right? And you just did a split on here. My guess is you would find that reducing the number of bins per input was less important than the number of splits in your tree.
Yeah.
And if you look at it from a regression point of view, the degree of nonlinearity is strongly related to the number of yes/no questions you can ask, right? Because your network is piecewise linear. So if you need a very strong nonlinearity, how many yes/no questions do you need to get a sine curve approximately, right? As an example.
Okay, so yeah, let's look at the answer from ChatGPT.
Okay.
Yeah, so ChatGPT first suggests that it is challenging to train a small network because it's hard to predict the optimal size beforehand. So ChatGPT prefer methods so we can train a large network and gradually reduce the size to see the threshold we need to keep the model have a good performance. This is the logic of ChatGPT. And the second logic ChatGPT have is that so it can be beneficial to have a large network to start with. So have help us to explore better solutions because we have a large search space and a large network typically have more layers, like deeper network can help us to learn more abstract, richer features from the data. So this is the answer from ChatGPT. Yeah, go ahead.
There's one additional consideration, though, I think, which complicates things, and this is the stuff that Ralph has been doing at Karlsruhe, where he has some evidence that when he trains an LSTM with too many nodes, that some of the nodes just end up canceling out the effects of other nodes.
Mm-hmm.
So yeah, we want to train large networks, but we don't want to train networks with redundancy.
Yes.
I'm not sure exactly how you do that because you have to somehow ensure that adding a new node doesn't just give you marginal improvement in performance, but ends up mostly just canceling out the effect of some other node. Yeah. So some kind of regularization would need to be in there, I think. Yeah.
Yeah, I think this is a good comment. I think one of the early work like on dropout. So they are like effectively training many ensembles of smaller network by removing some of the nodes during training. So this is like one way to utilize the large model. So we are training like a group of smaller models altogether.
If I'm just trying to recall in dropout, I know they drop out nodes.
Yeah.
Is there effectively anything like what happens in a random forest where you drop out inputs also? Because that would be interesting too, right?
Yeah.
Meaning you can still get predictions, but you want it robust. You want the predictors to be the ones which are most robust. And that if you drop out a predictor, it doesn't matter so much.
Yeah. In random forest, you can have the option to drop out a feature or have only subsample of your training data. There's multiple way of doing that. For yeah.
Ocean, I think there was an AGU presentation about that actually.
Okay. And what did they say?
It was the same time as my poster, so I didn't really look at it too closely, but it had adversarial in the name of the title. So, yeah.
Because my hypothesis is that if you do bagging in decision trees and you get random forests, there's nothing preventing you doing bagging with any other kind of neural network strategy, right? It's a fundamental technique. It's nothing unique to random forest. and that if you build an ensemble using bagging, you would get the same benefits for any neural network that you would get with a random forest, which is reducing the bias.
Reducing bias.
You reduce bias and variance, right, Luis? I'm trying to remember now.
No, I think it's increase bias, reduce variance.
Yeah, I'm pretty sure. Yeah.
Because what you end up doing is you end up using voting, right, or some kind of averaging mechanism in the end. So it's not clear to me that the overall effect is to reduce bias. You reduce overfitting.
Yeah, reduce overfitting. Yeah, increase bias, reduce variance. Yeah, but I have to look out.
But is the bias of the overall random forest worse? I don't think so.
I think if you have train a large ensemble of random forest compared to a large ensemble of cart, the regression tree, you will find a difference theoretically.
I think the bias should be reduced because you're averaging over many trees.
No, when
this
you
is the effect of
average, when you average, you're reducing variance, right? That's 1 over n.
Yeah.
But shouldn't you also reduce bias if you
the
if you
idea is
scale
bias.
bias differently? Yeah.
Yes, because each one of the trees kind of is already biased to a specific configuration. So in the moment that you are averaging all of them, you're canceling out the kind of bias that each one has.
But the trees are basically,
Unbiased estimators.
huge, right? Yeah, they're strong estimators. They're not weak like boosting.
I mean, why do we run ensembles in the first place? It's to reduce bias.
No, I think it's to reduce variance. The
Yeah.
reason that we have to have different features for each tree or split and different training sets for each tree is because we want to decorrelate the trees so that when you average over them, then you're reducing the variance. Because otherwise, then you have covariance effects between the trees, and that screws everything up.
Yes, but the decorrelation also reduces bias. I'm pretty sure there's theoretical results on this.
Okay, I'll try to look it up.
Yeah, or look.
But the theoretical result requires that the bias in the trees be uncorrelated. All right.
Yeah, I need to think more about this and look offline. Okay, so let's go back to the first question, so which is the fundamental question: so why network pruning is effective? So GPT provides 3 answers. So the first is can reduce redundancy because some nodes are really not important. They have very low activations in the prediction time. Yeah, for different, I mean, for all kinds of input, the node is not have very low values for because they have lower weights and lower bias. Second reason is that it can reduce generalization by remove overfitting, which I'm not very sure about what's the meaning of this sentence. The third one is can allow refinement to remove unimportant feature while make the important feature stronger. Like if you do iterative pruning and retraining strategy. So this is like 3 answers. I'm not very sure about the second one.
Yeah, I'm pretty sure. I mean, the thing that resonates for me is that you're reducing dimensionality of the problem. You're starting in a high dimension and you're progressively reducing dimensionality. But does anybody here know more about surrogate vector machines? Because my understanding is that one of the things with surrogate vector machines is that you can treat some of the, because you're doing a nonlinear transformation and you effectively, I've heard some comments to the effect of effectively you're doing an infinite dimensional representation. I'm not exactly sure what that means, but a surrogate vector, reduces it to a finite dimensional representation for learning. So the one that resonates most for me is this idea that you search in a higher dimensional space and then you reduce the dimensionality to the appropriate dimensionality for your problem.
Yeah, I think that's a good interpretation of this point. For me, the thing I struggle to understand is that by having fewer parameters to estimate, and the number of data you have is the same. So actually, you are increasing the risk of overfitting your parameters because your parameters are getting fewer and fewer. So the number of the degree of freedom is decreasing in your system. But my interpretation might not be correct.
Sorry, so the degrees of freedom going down, so what?
Going down, so you have more points, so it's more likely to
Sure.
overfit the fewer parameters. So it's like increase the chance of overfitting at the same time by removing overfitting at the same time.
Why would having fewer parameters increase the chance of overfitting? I didn't follow.
Okay,
Usually a
so
statistician thinks of it the other way around, I think.
yeah. Okay, so yeah, maybe my understanding is not correct. I'm sorry.
And another angle on this that's maybe different from the search space dimensionality would be the sort of lottery ticket hypothesis. I'm not sure. I guess I kind of view them as distinct arguments, where lottery ticket's more about, I don't know, it's kind of just introducing more sort of stochastic property into your initialization in a sense.
Correct. Yeah. But I think it's similar. So let's take a polynomial expansion in one dimension, right? So x is one dimension, x squared is another dimension, x cubed is another dimension, x to the power 4 is another dimension. You're going from one dimension up to higher and higher dimensions, right? And so if you started in x squared, x cubed, x fourth, and the system was in fact actually just linear, you would be learning weights on those 4 components. Yeah. And then pruning would be effectively saying some of these components are not as important as other components, and so I'm going to throw them away, right? That would be like the opposite effect. That would be the regularization effect. So if in fact it was linear, you should throw away the higher order terms. If it was quadratic, you should throw away the linear and the other terms, and so on and so forth. I mean, effectively, the question is, if I go from two variables, x and y, which is a 2-dimensional input space, and I go up to a 5-dimensional or a 10-dimensional space, what does that 10-dimensional space represent? It represents some, presumably, features of x and y, combination, some compound or nonlinear transformations or whatever, which we don't know what they are unless we actually examine the network to figure out what it did.
I think this is similar to SVM, support vector machines. So they
Exactly.
are
Yeah.
increasing the number of features.
But the problem in support vector machines is you have to propose the kernels or you have to learn the kernels.
Yeah.
And if you're learning the kernels, then you're actually not doing anything terribly different from standard artificial neural networks, with the one caveat that you're maximizing the margin, right? That's, to me, that's the unique thing about surrogate vector machines, is you maximize the margin so as to minimize the risk of misclassification.
Okay, so this is 3 questions I have. We discussed them. Then this is a conclusion. So the paper proposed a very effective method for compressing deep networks. So it can be reducing the model size by like 40 or 50 times while still maintaining the accuracy, like 3% of the original size of the small model can still have good performance. And I try to run some initial experiment by pruning LSTM networks for hydrological predictions. The result is showing that pruning also very effective for large LSTM-based networks, but we can just directly train a smaller LSTM network, which is equally efficient. So the future work is to explore more applications of deep compression and other technologies in hydrology. Maybe what we can do is to iteratively prune and retrain the weights, and we can also apply quantization technique and Huffman coding and other techniques to further reduce the size of an LSTM network to remove the unused gate, so we can have a better interpretation of the system. So this is the end of the presentation. So I want to thank the paper and thank Haoshen for sharing the paper with the group, and thank everyone for listening. We can continue our discussions on any topics.
So Yang, are you planning to follow up? Because it seems like very low-hanging fruit would be to just take the state-of-the-art LSTM that I believe is still Freddy's, and to just subject it to this and see what you get, right?
Yeah, I think I will do that, but I do not have time now. I have other project going on. Maybe I work on collaborations. Anyone who want to jump into this topic, we can collaborate. Yeah.
Can I make another small comment? Can you go back to slide 6 or 7 during the clustering explanation? Yeah, sorry, that was 9 or 10. A couple of yeah, another one. Yeah, this one. I was sorry, I was stuck on thinking about this. To figure out the first introits, they used it looks like expected value of the respective colors, and after retraining, so after refitting for the loss, it's different values. I was thinking about this as expected value is some sort of a center of mass of statistical distributions, but in the end, after retraining, they have different values, which means that the information center of that initial matrix is somewhere else. Do you have any ideas or any takes on how to achieve that in the first place? Even though I don't think it would show great performance improvements in figuring out this quantization, but I've just kept stuck on this. It seems like after retraining, the center of information, the center of what's interesting is somewhere else. It's not statistical, and I don't know if you have any takes on this or any ideas.
Okay, so from my understanding, the author also very interested in finding out the optimum centroid, the initial value to begin with, so that it can capture as much as information or at the first time step. So what they found out is that you have to keep the distance between the initial centroid to as much as possible. For example, if you can have a regular, somehow regular intervals between the largest and the smallest allowed number in these weights, the result might be better than just randomly picking the centroid. I think having more I think this means having more diverse weight, because the weights are so different in their values to begin with. This might help with generalization, but it's just my guess. I'm not sure about this.
Because I think it could, if we could achieve a better, but if like there was a way to achieve better precision on figuring out the centroids, maybe it would provide a better way of figuring out weights that can counteract themselves, as we were discussing with LSTMs, with some ways counteract the other. And maybe better quantization performance. I don't know. It's just a hot take. I don't know how much this is worth, but
Maybe we can do, yeah, we can follow up on this by doing different experiments.
I mean, here they're treating all the weights as being part of a high dimensional weight space, right? So if you got 10,000 weights, it's a 10,000 dimensional space, and you're clustering to try to reduce the size of that space. And then you're just trying to move the cluster centers around, right, while keeping that dimensionality reduction. There's some difference here between what Luis did. What Luis did was the weights were grouped together depending on which gate they were in, right? So you had the gates, you had the output gate weights, and then you had the input gate weights, and then you had the right. And if you kept them that way, then you would have to treat those each gate weight sequence as a vector. And now you would, and if you wanted to do clustering, you would have to do clustering on those vectors. Does that make sense? Instead of on the individual weights, you would now cluster on the vectors, and you would replace. So what Luis did effectively was a clustering on the vectors, and you replaced a lot of vectors from a lot of different catchments with one vector at the center, right? And another vector, and so on and so forth, right? Yeah. So presumably there are other things you could do besides what they did here, which was to completely not worry about what weights are related to what weights. In other words, they were not preserving any structure in the weight space, right? Yeah.
And so can any of this lead to some more interpretability of the inner weights of the model and how they learned and how they got to those weight distribution, those clusters you can figure out from the data?
I don't know about that, but this was one aspect that's been nagging me that does seem like you could improve on this approach for quantization. These authors are clearly much smarter than I am, but it also it does feel a little dated. Like this would have been trendy about 10 years ago. Not, clustering has issues with cursive dimensionality and all this stuff. So
Yeah, this is primarily about precision, right? Their focus is primarily about precision, because what they're trying to do, the guy's lab is TinyML. They're basically trying to say, how can I implement the same network with limited hardware? That's their main focus, right? So there may be other dimensions to this that we need to explore when we start worrying about interpretability, because I don't think they were caring about interpretability at all.
Yeah, and I think there are opportunities for more interpretability in this.
Yeah.
That's a hunch.
I mean, what you did, Yang, by preserving the bias terms, interesting. But it might be interesting again to treat the gate weights as a vector.
Yeah.
Think of them as not as independent weights, but as weight vectors, and then do clustering on weight vectors.
I just want to point to the link I sent, just the textbook by Trevor Hasty.
Hasty, yes, I got that.
Yeah, they say that the improvements in prediction obtained by bagging or random forest are solely a result of variance reduction. And also for all M, the squared bias of the random forest is greater than that of a single tree.
So
it is variance reduction.
yeah, I know that's what they say, but I remember seeing a paper, and I'm trying to reconcile with it because I'm not a statistician, I'm not an expert on this. I'm trying to reconcile this with the fact that I've seen elsewhere that ensembles, that when you run ensembles and then you calculate the expected value of the prediction from the ensemble, and then you compare that to your whatever it is you're trying to predict, that you can show that the overall error is reduced, Now, I understand that that's because you're reducing the variance, but you're also in the process somehow reducing the overall error. And if you're reducing the overall error, then that by definition means you're reducing bias. So I'm having trouble.
Well, no, it's just
reconciling.
you're increasing bias by a lesser amount than you're decreasing variance.
Yes, yes, I agree with that. But the average bias over all the individual ones is reduced. Okay, so that's what you're calling variance, okay? If you're
Yeah,
reducing the average
right.
bias.
It's been a while since I've read Hasty, but I think this is sort of just an easy. I get confused about this too, but the way they use the terms is a little different.
Yes.
They're used in other contexts.
So the
Well,
overall
if
mean
you think of
square, which is the squared of the squared mean plus plus the variance is reduced.
yeah. If you think about random forest predicting some kind of linear function, you often see that kind of the middle parts are done very well, but then at the extremes you have some bias, right? You have it all of a sudden just levels off, and
Yeah.
it's less than so that's basically where the variance is being reduced, and that makes the mean squared error happy, but oftentimes like KG doesn't like that because the
Sure.
variance isn't preserved.
Sure. Yeah, and we've known for a long time. I mean, this is just the inherent in the equation that that you can go mean can go up while the variance can go down as long as the total mean squared error is reduced.
But in the Hasty context, as well as others, when they're talking about this sort of bias variance trade-off, it's more of like talking about in sample versus out of sample.
Ah,
Right. Like and I'm sorry, I'm a little rusty, but they would say that a single tree is less biased, which I take to mean, it's able to overfit better within sample.
okay.
It's not going to generalize well. Like sort of out of sample, it's going to have greater variance. Hopefully I said that right, but that's what I meant when it's easy to get tripped up when you're talking about how terms are used in this sort of bias variance trade-off. I don't know if
Yeah,
that
this is why people keep reporting KGE, but that's not what I want to see. I want to see the bias ratio, I want to see the variance ratio, and I want to see the correlation because just the overall statistic to me doesn't mean a lot. Yeah.
Yeah, makes sense.
Are there other places in hydrology, just quick off the top of our heads, low-hanging fruit seem to be Freddie's LSTM, but are there, or anybody else's LSTM, are there other low-hanging fruit we can think of in our field where pruning and quantization and Huffman coding could seem to be, worth exploring, desirable thing to do right away?
Yeah, I'm thinking whether it can be applied to differentiable modeling, but I'm not sure how to do it, which is also quite popular framework now.
Because in some sense, I'm wondering about the relationship between early in training, you get a very rapid decrease, right? And then you get this flattening off. And how much of that flattening off is related to quantization issues, and how much of it is, related to just this the metric is insensitive to values of the weights, right? Because if you keep reducing your learning rate, effectively you're saying that I care about more and more precision. That's my interpretation, unless I'm wrong. But a small learning rate is effectively equivalent to saying high precision in my parameter space. When we talk about neat neuroevolution of augmenting topologies, which I want to do at some point, um, the attitude there is very clearly that the precision of the weights is less important than the learning the structure of the network. Yeah. So they put all their effort into the connectivity of the network and into the form of the activation functions. And when they do weight learning, they don't even bother with gradient descent. They just do mutations. Right.
So what's the size of their network that eventually?
They can get very rich output performance with very small networks.
Okay.
Because they're not using a layered structure.
Mhm.
So neat, you start with, let's say you have one input and one output. You basically just start with two nodes. And your network is just, the output is the weight times the input. That's the first network, right? Which is essentially just a simple multiplication or something. And if you have multiple inputs, then let's say you've got three inputs, you start with three nodes input connected directly to the output and just multiplied by a weight. And then you can do three kinds of mutation. You can do a weight mutation. You can do add a node mutation. Add a node means you split a connection and you add a node between the two. And you can do add a link connection. In the beginning, you can't add any links because everything is linked, right? Inputs to outputs. And so when you add a link, your link can be added between any input node, hidden node, or output node. So instead of building a multi-layered perceptron, which is the standard approach, you basically do something which you could argue is closer to what happens in the brain, which is any node can connect to any node.
Mm.
And you do that by mutation. So you learn a link. And so if you link backwards, for example, so you can represent recurrence by just linking backwards.
Mhm.
Yeah. And and then what they do is they grow those networks. And then, but the problem that NEAT solves is it says, how do you use crossover mating to grow networks? And they show that crossover is very helpful. But even without crossover, their method still gives very good performance compared to standard approaches.
Mhm.
And the reason, of course, they got into this is because they wanted to build small networks for robotics to solve robotics problems. So when I talk about that, I'll show some of their results. But it is interesting in the sense that it's in some sense closer to Kolmogorov-Arnold networks than classic networks. And I think if you combined NEAT with Kolmogorov-Arnold networks, you would have something very powerful. We need to talk about this, Luis.
Yes, in fact, I was thinking that in the moment that you're kind of splitting or adding another node inside of a link,
Yeah.
basically you are adding complexity in this connection. That is
Exactly.
basically what is doing Kant. That is
Yeah.
assuming that could be any complexity in this kind of connection.
Yeah, you're adding a nonlinear, the node is a nonlinearity, basically. Yeah, exactly. And they get very far with just rectified linear units, no, sigmoids, Gaussians, and sinusoids in their early work. I mean, I haven't looked at their recent work, but a sigmoid is a compression, a Gaussian is a symmetry, and a sinusoid is a periodicity. So they show that you can get very, very rich. Oh, and the other commonality with CANs, Luis, is so then they go to something called convolutional pattern producing networks. And what they show, similar to CANs, is that you can start with a very low resolution representation, and you can learn a model, a representation. And then you can go to finer precision resolution without having to retrain the model. So just like in the B-splines of the CAN, you can start with a low resolution and you can go to finer and finer resolution. So similarly in the NEAT, in the HyperNet and the convolutional pattern producing networks, you can start by learning a crude approximation to the problem. And then you can put in more resolution without having to retrain your network, but then you could retrain your network and you could progressively. Yeah. So it's a very different strategy, but I think it's very promising. Should be very promising for building hydrological models because we're trying to build interpretable models. So we want the nodes to be interpretable, right?
I think somehow linked to the like bottom-up approach, maybe.
Yeah. And so I think they've compared their approach to the opposite approach, which is by starting with very large networks and pruning. And they claim that, I mean, you'd have to do a lot, but they claim that it's more efficient, right? They're actually able to grow a solution. And that's actually where I got the argument about so what they're doing is they're progressively increasing the dimensionality of the problem. But they're not using gradients to learn how to increase the dimensionality. They're using genetic algorithms. So in effect, they can randomly try. They don't need a gradient to help them decide whether to increase a dimensionality or not. They randomly increase the dimensionality. And so you are able to get to solutions that you would not have got at if you only did it based on a gradient signal. But at the end, you end up with a very compact network because you don't have to pass through multiple nodes. You can just connect this one direct. It's like residual networks, right? Everything is a residual in a sense. You're just learning how to reduce the residual. Yeah. Somebody else put something in the chat. Oh, that was Tim. So that was very cool. Thank you, Yang. I'm going to have to think about other applications because it seems to me something similar should work even for image processing and all the stuff that people are using convolutional neural networks and all these things for. So.
Okay. Thank you, everyone. Yeah. Can continue the discussion